We've been trying to plot our course correctly for the past hour, but this damn deviation keep throwing us off. What are we missing here, second officer?
It's strange, sir. Every correction we make still puts us off track by a few degrees. I have recalculated the run lines, checked the distance, and it's not adding up.
Sounds like we're missing something on the map projection. The error grows with each plot. Sounds like a mystery.
나의 두 눈을 감으면 떠오르는 그 눈동자 자꾸 가슴이 시려서 잊혀지길 바랬어 꿈이라면 이제 깨어났으면 Oh no!
Captain, second officer, I have a small issue with the readings.
Not now, Cadet. We're dealing with a navigational issue here. Not unless you remember anything about Mercator Sailing.
Yeah, unless you happen to have a light bulb moment in that head of yours.
Mercator Sailing? Let me think.
12 seconds later.
Aha!
Flashback.
So, good morning everyone. Today, we're gonna explore Mercator Sailing, a key navigation technique used by sailors worldwide. This method is based on Mercator projection, a specialized type of map designed to help plot courses accurately across the curved surface of the Earth. The goal here is to keep navigation straightforward by using lines and angles that remain constant even in a flat map. Our agenda is to discuss the Mercator projection, Mercator charts, rhomb lines, meridional parts, DMP or difference of meridional parts, the triangle, and the formulas that involves in Mercator sailing. So that is the overview of our topic. Next is we need to know what is Mercator projection. So Mercator projection was developed by Gerardus Mercator, a 16th century cartographer who wanted to help navigators to follow a straight line path more easily. This projection turns the round Earth into a flat map by stretching the globe into a rectangle. On a Mercator chart, latitude lines are shown as straight and parallel, which isn't how they appear on the actual globe. Longitude lines are also straight and equally spaced. This is quite different from a globe, where they get closer together near the poles. These setups makes direction easier to follow because all angles are preserved, even though distances get stretched more as you move away from the equator. So why the distortion? Because of the stretching in Mercator projection, objects appear larger as you move farther away from the equator. Greenland, for example, looks enormous on a Mercator map, even though it's much smaller than it appears when compared to places near the equator like Africa. This distortion is intentional. It's what makes the straight line sailing possible on this type of map. Without it, navigators would have to constantly change direction. Next is, so this is what I'm saying about the Mercator chart. Next is rhomb lines. Run blinds are loxodromes. Imagine you're steering a ship and you want to maintain a constant compass direction. A run blind allows you to do this by crossing all lines of longitude at the same angle. On a globe, this line would be a curved path, but on a Mercator map, it looks straight. This makes a run blind the ideal path for consistent navigation, as you don't need to adjust your course. However, keep in mind that while a straight line on the map is not the shortest route between 2 points, the shortest route would be a great circle path, which we'll cover separately. Next is meridional parts. To help with the accurate distance measurement and a stretch Mercator chart, we use something called meridional parts. These are calculated values that measure the north to south distance from the equator up to any given latitude. Because the Mercator projection stretches everything, we need meridional parts to adjust for the actual distance we're traveling on the Earth's surface. So meridional parts are listed in nautical tables. So if we know the Earth latitude, we can look up the corresponding meridional part value. This value tells us the stretched distance north to south on a Mercator map, ensuring that our navigation is accurate. So here is the meridional parts formula. We have the log tangent of latitude multiplied log tangent multiplied by the latitude divided by 2 plus 45 multiplied by 7915.7 minus the sine of latitude multiplied by 23.269. So next is the original part table. Next is the difference in original parts. So the DMP gives us the distance between two different latitudes. Say you're traveling from one point in the northern hemisphere to another farther north. The DMP helps you calculate how far north or south you've traveled, accounting for the distortion of the map. So this is the Mercator Sailing triangle. To simplify, the vertical side is the difference in latitude or the DLAT between our start and the endpoint. The horizontal side is the difference of longitude, how far east or west we've traveled. And the long part, the hypotenuse, is the direct distance we're calculating representing by the rhomb line on the map. With this triangle, we apply trigonometry to determine the exact course angle and distance, helping us keep on the correct path. Now for the important formulas here.
End of flashback.
I remember now. Mercator Sailing allow us to plot a constant compass direction as a straight line, but we need to account for the distortions, especially as we're heading closer to higher latitudes.
Go on.
We could be seeing deviations because we're approaching a latitude where the distortion is more pronounced. We might need to replot the course with compensation for the increased distance covered on the chart.
That actually makes sense. We've been trying to correct it without considering the effect of the projection distortion.
Well, Cadet. Seems like you've got something in that head of yours after all. Why don't you plot the course adjustment then?
Yes, sir.
Wow!
Well, I'll be damned.
Thank you, Captain.
Not bad for a wind sensor issue, huh?
Go. Luckily, I remembered, sir.
Alright, now let's deal with that wind sensor unit.